We're taking a look at question number 2 in topic 6.5. This is calculate the amount of energy needed to boil 91.2 grams of carbon tetrachloride. Boiling point is 350 Kelvin. So they give us enthalpy of fusion and they also give us enthalpy of vaporization. So the first thing I guess to figure out is the phase change we're going through is from liquid to gas because we're boiling it. So we're going to be using the enthalpy of vaporization. We can ignore the enthalpy of fusion because we're not melting or freezing. We are looking for the energy needed. So looking at the unit for the enthalpy of vaporization, I see it's kilojoules there. So I'm going to go ahead and assume we're looking for energy in kilojoules. Let's start off with the fact that we have 91.2 grams. So we're going to start off with 91.2 grams of carbon tetrachloride. And we're going to treat this just like a conversion problem. We're going to go ahead and convert to moles. So remember, the first thing you do when you're in doubt is go ahead and convert to moles. We have the molar mass here, and remember that's a flippable conversion factor. So we know that 1 mole of CCl4 has a mass of 153.82 grams. That will allow us to get grams to cancel and convert to moles. Then, knowing the enthalpy of vaporization, we know that 1 mole of carbon tetrachloride will vaporize by adding 30.0 kilojoules of heat. And then our moles cancel out. So going through multiplying 91.2 times 30 divided by 153.82, we're going to come up with about 17.8 kilojoules of heat will be needed to boil 91.2 grams of carbon tetrachloride. Let's see here. All right, 3 significant digits. My measurements are all 3 significant digits, especially at the beginning. All right, let's take a look at question 3. Question 3, we want the heat of fusion for water is given 6.01 kilojoules per mole, and the heat of vaporization. How much energy is needed to melt 22.5 grams of ice? So again, you have to decide, do we want heat of fusion or heat of vaporization? And melting and freezing, that is all about the heat of fusion. So we're going to use our 6.01 in this case. Same thing, start with your mass, convert it to moles. So 22.5 grams of water, ice, I guess, at this point, and the molar mass, 1 mole of water or ice is going to have a mass of about 18 grams. And then last but not least, we know that we can convert 1 mole of water, or I guess ice, into water by providing 6.01 kilojoules of heat. And grams cancel, moles cancel, and we're left with kilojoules, 3 significant digits again, 7.51. Okay, on to question 4. I think we looked at this one or something similar to it, but it says how much energy is needed to heat 36 grams of ice from negative 10.5 degrees Celsius to water at 22.5 degrees Celsius. And they give us a bunch of specific heats. So I think the big thing, I'm going to zoom in here, is to recognize that we're starting at a low temperature. And I know this is not going to be to scale, but we're starting at, let's see, negative 10 degrees Celsius. And we know melting happens at 0 degrees Celsius. And then we're actually heating it up to over 0 degrees Celsius. So we're heating it up to, what does it say, 20, where is that? 22.5? 0.5 degrees Celsius. So this isn't really to scale very well, but just trying to give you an idea. Our first area right here, we're actually changing temperature. So we're going to look at calculating Q for that area first. Then in the second area right here, we're going through just a phase change. So we're going to have to use the enthalpy of fusion there. And then the third part, we're changing temperature again. So we're going to use Q equals MC delta T. So going back to our problem, let's see here. All right, so we're going to go ahead and do Q1 first, and that is how much energy do we have to add just to get the ice to go from -10 to 0 degrees Celsius. So the mass of ice that we have is 36 grams. So 36.0 grams of ice. And since we are looking at something that's a solid, we're going to use the 2.108 here. So 2.108 joules per gram degrees Celsius. And we're putting heat into it. So you should think ahead that this is probably going to be endothermic. But if we think about our temperature, our final temperature we want is 0 degrees Celsius. And our initial temperature is negative 10.5 degrees Celsius. And that's what gives us our positive temperature here. So our delta T right here ends up being 10.5 degrees Celsius. So our Q to three significant digits is 797 joules. You can see grams cancel, degrees Celsius cancel, and you're left with joules. So that is how much heat it takes just to get from -10 to 0. So now we're going to take a look at this little area right here where there's no change in temperature. And when there's no change in temperature, we cannot use Q equals MC delta T. We're going to use Q equals the number of moles times the enthalpy. And in this case, because we are melting it, we're going to be using, let's see, the enthalpy of fusion for water. And so I'm going to go ahead and put this all together. We know we have 36 grams, so let's go ahead and start with that. We have 36.0 grams of water. To convert that to moles to get our N, we're going to go ahead and use 1 mole of water. And oops, I don't know why that crossed out. Didn't mean to do that. There we go. Okay, oh, let's try that again. I don't want that on there. Yeah, delete that. All right, let's try that again. So let's see, 1 mole of water over 18.0 grams. That's going to convert us to moles. And then from an earlier problem, we know that the enthalpy of fusion for water is 6.01. And remember, that's kilojoules. That's important. That's per mole of water. And then I'm just going to convert to joules right here. There are 1,000 joules, move that over, for every 1 kilojoule. So I'm going to put that all together. Grams cancel, moles cancel, kilojoules cancel, and I'm left with joules because I want it to match what I got in the first part. So just converting that 36 grams, by the way, that's 2 moles. If you look at this number right here in the 18, you can see that that's 2 moles. So this number should hopefully make some sense here. We come up with, let's see, 12,020 joules. So 12,020. And I'm going to just keep track of the fact that this is my significant digit. I should have 3 sig figs here. All right. Our last step is just to figure out how much heat we had to add to get it after it's all melted to go from 0 degrees Celsius to 22.5. All right, so this is going to be my Q3. Q3 equals MC delta T again. So the mass, 36.0 grams. And this time we're going to use, up here, we're going to use the 4.182 because that's for our liquid. Water, because at this point we're all liquid. So 4.182 joules per gram degrees Celsius. And the change in temperature this time, our T final is 22.5 and our T initial was 0 degrees Celsius. All right, let's see here. So when we plug that into our calculator, I ended up getting 3,000. 390 joules. All right. And again, three significant digits here. So we're going to find Q total. This is easy. So Q total, we're just going to add them all together. So Q total is going to be Q1 plus Q2 plus Q3. And when we put that into our calculator, we get around 16,207 joules. Um, that 2 right there is my last significant digit. So we're going to say 16,200 joules or 16.2 kilojoules. Both of those answers would be perfectly fine. All right, I know that's kind of one monster of a problem, but take a little bit of time, take a look at it. The numbers aren't that bad to deal with, so could be something you see. And then the last problem here, we're kind of back to normal. We've got naphthalene, which is that stuff that smells in mothballs. They sublime at room temperature. So sublime, remember, is going from a solid right to a vapor, not going through the liquid phase. So they give you the heat of sublimation, which is something we haven't seen, 72.9 kilojoules per mole. How much energy is needed to sublime 15 grams? So we're going to take our 15 grams of naphthalene, and we know that 1 mole is equal to 128.17 grams. And then we know it is 72.9 kilojoules of heat needed to sublime 1 mole of that stuff. So grams of naphthalene cancel, moles cancel, we're left with kilojoules. And again, three significant digits, 8.53 kilojoules. And that's it. That should look pretty familiar. It's just looking like some conversion factors again. So just, watch your units and let your units walk you through the problem.